Anyway, thanks everyone for joining. Today we have two very interesting talks on neurosymbolic AI. We're still waiting for the other speaker to join us, but we'd like to thank the speakers. Our first speaker is Louis Lamb, and as you know, Louis has been pretty active in this field of neurosymbolic AI. And in fact, one of the papers that he wrote in the Artificial Intelligence Review about a couple of years ago has almost 1,000 citations on this area. He has a lot of good insights into it. And then I will let Louis talk right now. I believe Louis with Catholic University.
Yes, yes.
And I will let Louis start his presentation.
Thank you so much for the invitation. It's an honor to be here, and I'll try to bring a glimpse of the field for those who might not be very familiar with the areas, and I'll try to be comprehensive. I know it's hard to be in half an hour, and I'm trying to bring as well some insights from what's happening in industry with respect to neurosymbolic AI, and how we can see that the field is becoming more and more attractive, and in a way is gathering more attention from different areas or sub areas of AI and computer science. So in the talk, I give some basic concepts, introduction, evolution of the field, how integration of learning and reasoning is coming to the fore, is getting more and more attention, especially because we have very successful applications of machine learning, but however, we see a lot of limits in terms of the reasoning capabilities of the tools that have become very popular these days, not only in industry, but across the spectrum in other fields. What kind of approaches for neurosymbolic AI we have, and what is conceptualization of neurosymbolic AI? And some perspectives that I hope we can discuss in a more informal approach as well. So if you want to read or have an idea of the field, I think Ran mentioned about this paper, the second paper that we wrote some years ago, and still very up to date in terms of the trends and how the field is being organized over the last years or the last decade. And also there is an interesting paper as well that looks at some formal aspects, this mathematical framework and learning techniques for neurosymbolic systems, that I think it's an interesting paper that's also being posted on arXiv as well. So the big question in AI has always been the first one, I believe, at least for some of us. We have been investigating if digital machines can think. This is not a novel question, right? Even before electronics, Pascal, Leibniz, and other researchers and mathematicians, engineers, they have been asking if we could build artifacts that would mimic the way that we reason, or they show some cognition. And this was a big question around the times of Turing, and then in the late 50s when AI came to the fore after the famous Dartmouth meeting organized by McCarthy, Minsky, Shannon, and other luminaries of the field. And coming to a big jump to today, where we are using these large language models, Gen AI. So one of the questions I did a few weeks ago were, okay, are you neurosymbolic? And I asked them if they were, and these are the answers they provide. Gemini is not a purely neurosymbolic AI system in terms of architecture. You can ask the question yourselves. You might get a different answer. But these systems that we've been using these days, Claude, I also asked Claude and other AI models, language models, if they are aware or if they are neurosymbolic. And the answer I got today, this morning, just before the talk, about an hour ago, I was saying, okay, let me ask Claude again if Claude is neurosymbolic or not. And the way that Claude sees itself, it's not neurosymbolic AI in the technical sense, but it gives a long explanation about why it behaves as if Claude was reasoning or proposing a way of reasoning versus pattern matching in the way. So at least I think they have been programmed to respond that they are not purely, or they are not effective neurosymbolic systems in the way that we see systems where reasoning and learning have a semantic component that's crucial in the sense of building sound AI systems. So we are not there yet. So we have to go back and keep doing our research, the hard work in terms of research. Okay, let me pause a little bit and mention that this integration between learning and reasoning is not only a subject that has received attention recently, but in history, yet already in the 1940s, when Macaulay and Pitts proposed their first artificial neural network model, soon after that, researchers like Stephen Klein is well known for his studies in regular language, in finite automata, and other results in recursion and computability theory. One of the key motivations for Klein to study finite automata was to analyze what kind of events neural networks of Macaulay and Pitts were processing or computing or identifying or recognizing. And so one of the key papers that Klein published, and even McCarthy at the time, was to analyze, what kind of reasoning, what kind of meaning the proposed neural nets that they had at the time were capable of represent, compute, or learn. So this question is actually not new. This question is a question that has been around in science with other disguises, with other, let's say, presentations and other abstractions. But coming to more modern times, the reality is that we're living a time where technology has, dominated our lives in terms of not only the impact that we have in our research world, in our academic life, or in our professional life as computer scientists or engineers, but AI and computer science have been even recognized as very valuable fields of scientific discovery, even more so. And even, it's a very strong recognition that we received in terms of the Nobel Prizes in 2024. Both the Nobel Prize for Physics and the Nobel Prize for Chemistry recognized artificial intelligence AI research and the results that we are bringing and the paradigm shifts that we are bringing to, let's say, to the hard sciences, to the sciences that historically have been considered, let's say, the prominent sciences that we have in the world: physics, chemistry, medicine, biology, and so on. So AI has now an impact that goes well beyond our small community that we had, let's say, up to 20 years ago, when AI or machine learning and the related fields were considered like niche fields, even from a computer science perspective. If those who have been around here for more than 20 years will remember that even the subfield of AI was, let's say, one of the smallest, or not one of the smallest, but a smaller division of within computer science. But the reality is that AI has had a huge impact. And the impact is being compared to the impact that the web had from the 90s, when we started using networked computers via the internet, using the web technologies that provided us with a much easier interface, with much easier communication mechanism to communicate between humans and communicate between people in companies, people in education institutions, and so on. Right. So I'm trying to move into neurosymbolic AI. And another motivation for neurosymbolic AI is that the current technologies, as powerful as they are, they have limits. And from time to time, we see some news in the media, in specialized media, saying that some people get surprised by some of the limits that, say, the purely neural approach or purely machine learning approach of AI has. And in particular, this news here, it caught my attention because a well-known phenomenon when you work in automated reasoning, theory-improving formal systems, is that dealing with negation is something hard to deal with. Those who have ever tried programming in Prolog know that dealing with negation requires some special.
Luis, can I
Yes.
have a minute of it? I think
Yes, sure.
you should put your stuff in the presentation mode. That's one of the comments.
Am I not in the presentation
No,
mode?
you're not in the presentation mode, I think.
Oh my God.
Yeah,
I
yeah.
see the presentation model here. Okay.
Maybe
Yeah,
you
we
change
see your speaker notes. We see your speaker notes.
Oh, no problem. Oh, you're seeing the speaker notes because we are in between friends. There's no problem that we're seeing the speaker notes. But I'm gonna try to increase the size here. Just a second.
I think maybe you are using two displays. Oh yeah,
Oh yeah, maybe I'm using two
if the
displays.
two
Let me
displays,
just.
then you have to
No,
switch
no,
the
no, no.
display. Otherwise, see, it's showing
Oh, that's a
it is
pity.
showing
You
the
could have told
presentation
me
mode.
before. Yeah, 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 yeah. I always use two displays,
Yeah, that's the problem.
Old habits of a former computer programmer.
Mm.
Okay. Just a second here. That's a pity. Desktop one. What can you see now?
Go to the presentation mode.
No?
No, it's still the same thing. And the reason is that swap displays. Look at the slab. Okay. Uh,
Yeah,
Go to the presentation mode.
yeah, 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 yeah.
And then this is then
Uh,
you'll see a swap displays. Do
oh,
that.
yeah, yeah, yeah. Just a second. Presentation
On the top.
mode,
Yeah,
swap
there. Yeah.
displays. Can you
Yep.
see it
Yep.
now?
You're okay now. Yeah.
Oh, okay. Oh, sorry about that. I apologize. I thought it was okay. Okay. So one of the things we have to pay attention to is that now it's okay, right? I hope
Yep.
it's so.
Uh-huh.
Okay. Oh, sorry about that. I apologize. So one of the things we see is that there are limitations, and especially when you see the news, some surprises like, some Gen AI tool not being capable of dealing with negation, and then people start to realize, oh, well, why can't these tools deal with negation? And then people start to go back, and then they say, oh, people who work in symbolic AI, they've been facing this problem with negation for 40 years in automated theory improving in programming languages and in logic programming and so on. And so people realize the reason, oh yeah, 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 we need other tools other than only focusing on deep learning based approaches, right? So, and this kind of thing bring to the fore the need for us to be a little bit more careful in the ways that we develop current AI systems, to have systems that are more reliable and actually are more trustworthy in sense of applications. If we think here in terms of medicine, and here is, it's clearly a medical image analysis based on a visual language model or on a visual model that's not capable of providing the right diagnosis if the doctor or the user starts interacting with this tool and provides some sentences and some questions that contain negation, which is very common in human discourse, right? And the point here is that neurosymbolic AI then offers this solution for for some or for a large class of these problems, because we can bring techniques that have been developed for many years in computer science that deal with automated reasoning, deal with formal reasoning, and then we can learn how to reason formally about these very powerful tools that we have and that are based on the transformer model or based on neural networks. And that's the whole point of the research that we have been doing. We need self-explained architectures. We need systems that are interpretable by constructions, or systems that are at least explainable, that you can explain their behavior. That's where neurosymbolic AI can provide an interesting contribution. So just to give you another following up where the area comes from. And just to remind that in the early 2000s, even neural networks were not that popular in the AI community or in the computer science community. Even at the New Reaps conference early in the early 2000s, neural network papers, they were, let's say, a minority section if you compared with, kernel methods, with SVMs, Bayesian learning at the time. And we had some very interesting results provided by Jeff Hinton and some people that work in this community that prove that deep belief nets and deep neural networks with several layers of neural networks could provide and could enhance the performance of computer vision, pattern recognition algorithms, pattern recognition systems, and so on. And this is the history of how deep learning became very popular, right? And today we got to the point where we had these very powerful language models, but another point that people make is that it's becoming more and more expensive. The energy footprint, CO2 footprint, and the use of energy, the energy requirements, and the cost of training and maintaining these models is becoming really exponentially higher. As you see here, from the beginning of the very large language models that we had about 6, 7, 8 years ago to today, the cost of only training these models is in the hundreds of millions of dollars. So this is becoming very expensive, and maintaining and operating them at inference time, at running time, at the deployment time, as we do in industry, is getting very, very expensive. And even the companies that are developing them, they are still in the investment phase. They're still gathering more and more capital to invest in these models, but they are not seeing the profits at the moment, right? So there are needs for not only from a cost perspective, from an energy perspective, but also there are other issues associated with security, safety, reliability of the models. This is a report. This was published in the AI Index report, and companies that have been using novel and modern AI technologies, they face several challenges with respect to safety, to security, to kind of incidents that organizations face when they deploy AI in an industrial setting. So there are several aspects that around modern AI that motivate the use of more formal techniques, of techniques that use automated reasoning approach, the techniques that strongly integrate learning and reasoning, integrate neural networks and logical reasoning, or that use theorem provers, combine hybridized with other language models like Amazon is doing, like other companies are doing, and that I hope I can illustrate some examples coming forward in the presentation. So in the end, the point that I wanna make here is the point that we have to know why technologies work. And technology becomes successful when scientists can explain why do they work. The recent Nobel Prize for Economic Sciences, the latest one in 2025, was given exactly to researchers that investigated why some technologies become influential in the economy. And some of the conclusions that they got is that the economy accepts, or the economy absorbs technologies and goes into a transition phase where these technologies become very useful when we are capable of explaining them and make an economic sense, not only an economic sense of the technologies, but also we can explain why scientifically they are robust and why we can use them over time. Right? So the Industrial Revolution happened after we could explain how electricity worked, how the engines work, how we could distribute energy, because we had a complete control of the scientific underpinnings of electricity and magnetism that led to the scientific revolution. And that's the expectation that we have about AI. From a more technical perspective, how we integrate learning and reasoning. Recently, also, people have been drawing analogies between this dual process theory of Daniel Kahneman that, popularly, I'm overly simplifying here, organizes the way that we think in terms of cognitive processes into systems. One system is a very fast system that recognizes patterns that we've seen before, that we immediately react when we are in danger, or we automatically do tasks that we've been training our whole lives, like crossing the street, for instance, or driving a car, things that we do automatically after a long period of training. And whereas system 2 is more reflexive, when we are confronted with new situations, we have to stop and reflect. When you are learning a new language, when we are trying to prove a new result, when we are conducting a new experiment in a lab, or when we are doing scientific research, we stop and we think and reflect. It's a much more reflexive system. So this system 2, system 1 have been, drawn a parallel or an analogy between Kahneman's system 1, 2 dual process theory and the theory of neurosymbolic AI systems. And this also brings some analogies with the schools of AI over the years that we had in terms of symbolic AI, here represented by Alan Yu and Herbert Simon. As you know, some of the pioneers of AI, they invested in theorem provers, in symbolic systems. Later, we had the school based on neural network theory and on neural learning. But we also had people who operated in between. We can say that Les Valent, over in his work on pack learning, on his work on integrated learning and reasoning, always saw the value of integrative approaches. The same way Judy Pearl, in his work on causality, he also saw the need to integrate symbolic techniques, Bayesian techniques, with machine learning to have systems that were more robust, right? And in our approach goes in a way that we want to develop tightly knit systems where the neural network itself will be both the learning engine and the reasoning engine. And in order to do so, what we did was to investigate what kind of logics neural network models could process, neural network models could learn. Another requirement that we saw in our research that we identified is that we don't need only to represent information that is static, information that is represented by propositional logics or by first order logic or by predicate logics. We saw a need in computer science, in AI, of representing a temporal dimension, in represent a knowledge dimension, in represent several different modalities. And that suggested to us to use or to identify ways of representing modalities of reasoning in neural networks, or at least to investigate what kind of model logics, what kind of model reasons we should be able to represent in a neural network to have richer system, a system that not only represented classical logic that has its own limitations, that has been designed with a very specific purpose, but other computational logics that have been designed more aligned with the needs of computer science. So this was the motivation of our initial work. So the idea here, for instance, if we think in terms of neural networks, was to identify if neural networks could be the proper framework to represent, or how to identify in what ways artificial neural networks could represent, for instance, the knowledge expressed by model logics, right? The relations between agents that interact in distributed systems, how we could represent the knowledge of those agents. And what we are capable of doing at the time was exactly to show that there are ways of constructing neural networks where you can have fragments of model logics, or even fragments of what we call, and which is technically called model logic programming, which is an extension of logic programming with model operators. And in this way, you can represent the knowledge of agents. We can even represent the interaction of agents and agent exchanging knowledge using communication mechanisms that we can design using neural networks or neurosymbolic agents as an architecture to represent each individual agent that interacts. In that way, we are capable of representing, and we are capable of showing that neural networks can indeed solve certain test beds or certain benchmarks for multi-agent interaction. If you remember the book by Ron Fagan and Joe Halpern, the late Joe Halpern, Moshe Vard, and Yoram Moses, they wrote this great book on reasoning about knowledge. Is a book where they explain how multiple agents or multi-agent systems exchange information and reach common knowledge about solving certain problems. What we tried to do in our research was exactly to see if this approach that they developed could be extended to a neurosymbolic framework where the agents not only were capable of doing deductions and reaching common knowledge or common agreements about the solution of a problem. And if you think in terms of the Muddy Children puzzle or other puzzles that are typical of the multi-agent systems literature, we're capable of showing that not only a neural network-based engine could solve the reasoning problem, but could also learn and improve its performance over time. Right? So our approach was based in this principle. Let's not only bring the classical results, or the results from classical logics and from predicate logics into a learning perspective by designing neural networks or algorithms that can learn, let's say, first order logic or fragments of first order logic. We are aware of the undecidability results that we have around that. That's why we work with fragments of logics. But also we are trying, and we organized or we developed a way of learning different model logics, or different logics that could deal with the knowledge of agents, with the uncertainty of agents, and with the knowledge of agents that evolves in time, right? So this was the key motivation for our work. And from an industrial perspective, from an application perspective, about a decade ago, one of our students did his PhD thesis on a work that was very pioneering for the time. I think it was way too ahead of time. I think he was one of the first researchers who were capable of integrating a learning engine with a model checker, right? So in that way, what the student did at the time in his thesis and later in the publications around 2010, 2011, or 2010, 2012, was to show that he could use, right, a learning engine to use the counterexamples provided by a model checker to refine the specifications of the model. In that way, we would have an adaptation engine that could improve the model specifications or the system specifications of a system and of a given software system or a given hybrid system or a given complex system. And we could use learning to automatically improve the specification, reducing the manual labor that we have when we are specifying properties of a system or when we are defining a model of a system. And to my surprise, I've been reading several papers in software engineering that are now adopting exactly this principle. They use counterexamples from a model checker or from a verifier or from a certain tool. And this counterexamples is now used as input into a language model or into another learning engine exactly to refine the model specification. So already about 10, 15 years ago, we showed that this was a possibility in terms of a potential to have neurosymbolic AI contributing to crucial applications in software development, in software verification, and in program verification. Another important application that we see in industry today of neurosymbolic AI is the work that Amazon and other companies are doing. They are using they call their approach neurosymbolic, but what the Amazon is using is that on top of their language models or on top of their Gen AI applications or their heavily intensive machine learning systems that they have with the data, you can imagine that the quantity of data that Amazon has, they use a theorem prover to guarantee that the outputs of the systems will behave with respect to the specifications at runtime. And this is very important because one can imagine that Amazon and some of the very large companies, they are, for instance, analyzing credit scores, they are analyzing behavior of customers, they are analyzing fraud at runtime, and they have to provide guarantees that their systems will behave and will be solid or will be trustful, from the perspective of not only the company, but also from the perspective of those who are using the systems. And they have to provide guarantees that the system will operate at runtime with the same guarantees and the same stability and the same precision that purely symbolic systems work. So now neurosymbolic AI is getting also attention with respect to companies that have noticed that there are the need to guarantee that the behavior of this huge AI system that we use today are providing the answers that we want with the level of precision of the accuracy that are needed in terms of deployment time, in terms of inference time, right? So finally, another example that I want to bring here to the fore where neurosymbolic AI is also gaining attention is that according to certain mathematicians and Terence Tao, who is very well known from UCLA, Kevin Buzzard and other mathematicians, they are seeing a lot of value in AI techniques to help them improving and in advancing mathematics research. And one of the systems that can be used by let's say in general, is those systems that the Google DeepMind has developed, for instance, alpha geometry. And it's also a hybrid system where on top or aligned with or combined with the language model or the system that's based on neural networks, we have also a symbolic system that uses hypotheses that are created or generated by the neural network-based engine. And these hypotheses are used as lemmas to construct new results and to prove new results about certain domains. So here there also has been identified a way where neurosymbolic techniques not only can provide insights to research, but can also, to research and to commercial applications, as I mentioned before, but can also provide insights and tools to advance mathematical research, to advance scientific research. And as we know, scientific research is even more rigorous than certain or than I would say than any other so let's say, domain of human life, because we are always testing hypotheses using the scientific method and using rigorous techniques to guarantee that the results that we are producing are reliable. And neurosymbolic AI techniques have been shown to be useful in advancing mathematical research, which is something that we believe is in another quite relevant result of recent times. Right. So unfortunately, I do not have enough time to go over all the slides, right? So I prepared the slides for a longer time, but I just want to conclude here saying that in conclusion, neurosymbolic AI represents an opportunity for a paradigm shift in artificial intelligence research, in the sense that now not only you can use powerful deep learning systems or machine learning systems that provide some very interesting results in terms of pattern matching, computer vision, in terms of language, translation, language use, but what they lack is a semantic understanding and a rigorous understanding of how the reasoning process happens, not only in our cognition, but also in the scientific disciplines of logic, computer science, and mathematics. Neurosymbolic AI can be seen as a way of unifying learning and reasoning. In that way, we provide explanations or interpretations for systems that are built with interpretability by design, or we can use neurosymbolic AI to try and build explanations post hoc. That's not my preferred way of interpreting and understanding systems, post hoc explanations. I would rather build systems by design that are interpretable and therefore explainable as well. And also neurosymbolic AI, given the results that we bring from logical systems, from the computational logic community, it can also be a tool that help us to show properties or verify properties of the systems in a way that we can build more trustworthy AI systems. So that's why we say that neurosymbolic AI, or let's say the third wave of AI, is a way of combining not only the neural network approaches that are dominant today, neural network-based approaches that are dominant in industry today, but also we can bring, let's say, the full history of computer science results that we have in rigorous logical reasoning, in rigorous computational logic, that can clearly benefit artificial intelligence research, artificial intelligence applications, in the same way that problem verification and automated improvement have benefited other fields of computer science and AI.